Okay, so what we have seen up to now is, so we have begun with a very general definition of conformal field theory using a very abstract definition. Then we have seen actually an example. So we have seen that this definition is not, it makes sense in the sense that there is at least one example of such CFT. We have seen also that using this definition, actually, we can understand a little more the fields, and we can understand a little the correlation function of the fields. Okay, but still, even if we have some example, I think it might be still blurred to you, like what is the meaning of the T? What is those T? What is those fields actually? Where do they come from? Even if, well, we have seen that the fields at least, well, they should come from some kind of statistical model. Okay, we have seen that. We have taken the bosonic free field, and we have seen that in fact the correlations are not just like given like that. It's not just, you know, some random guy who decided, okay, I defined this. It can have actually been seen as the scaling limit of a system, which is the discrete Gaussian free field. Okay, so last time we have seen that we can consider the Gaussian free field, the statistical model, and then we can look at some big product of derivatives of any order, and then we've shown that, well, if we scale those guys, well, then we have a limit of the correlations, here correlation meaning just the expectation of the product of the thing inserted at different points. Okay, and so we have seen the importance of two things. Of first, this kind of recipes that I can like put kind of everywhere, you know, I can translate everywhere on my grid. Which were those kind of products of derivatives. We saw also that such objects actually need not only the value of the field phi at the point x, but also around this point. And we saw also the importance of doing the scaling limit of that, which means that I had to multiply by delta to the power minus something. And I told you that this something, and we saw it in different example, that the something actually in the power actually is the scaling dimension, which is the sum of the left and right dimension of the continuous limiting field. Okay, so we have seen that, okay, there's at least one example where we have a probabilistic interpretation of the conformal field theory. So now what we want is, well, there is two kind of question one can ask is, the first one is, can we do the same with other models? Okay, so can I take like any other model and can I show that, okay, there is convergence toward a CFT? Well, this question is actually very hard, and we are not going to see this part. And what's more, so for two reasons. First of all, it's not known for a lot of models, actually. Like mainly it's known for the Ising model, but and the Gaussian free field, but not for the others. And for the Ising model, actually, it would take like a whole lesson actually to show that actually. So instead of that, what we really want to do, I mean, what I really want to do and what I really want to convey, it's the following fact. If I have a model and if I kind of know that there is a scaling limit, how can I guess that indeed the scaling limit is a conformal field theory? Like if I look at my discrete model, I mean, what kind of properties must have this discrete model such that, okay, at the end I can say, okay, if there is a scaling limit, then it should be a conformal field theory, okay? And then we will see later that, well, we'll have a certain property on this conformal field theory, which is called the unitary, which will come from the fact that we are considering a statistical model. So the fact that we have really a probabilistic model will lead us to a property which is called the unitary property for CFT. And we'll see that actually, not only will we be able to show that, well, the limit of such kind of model, if it exists, should be a CFT, but actually we will be able to specify which central charge it should be and what are the dimensions of the different fields, okay? So it's more this thing that I want to do, okay? So it's not really showing that I have convergence to a CFT, but more to try to understand the axiom of CFT coming from statistical model and what do I need on my statistical model so that I have a CFT at the limit, okay? So already this is really the main question. So can we gain some insight on the axioms of abstract CFT by just looking at the statistical model? And we'll see that indeed we'll be able to understand better actually the transformation law, first of all. You know, I told you that the field transform, but why? Actually, in abstract conformal field theory, this transformation law is really just, you know, an equality of correlations. Okay, but we don't really understand why really we should change the fields. Okay, and typically I hope that by using the statistical model, you will really understand why actually we should change the fields indeed. Okay. Okay, and we will see also what does it mean to have a conformal symmetry, because when we look at the conformal field theory, the abstract version, actually, there is really, I mean, I think that like it doesn't convey the notion of conformal symmetry. I mean, what is this conformal symmetry? Okay, so indeed we have seen that there is some like equality between correlations if the map is like a Mobius or thing like that, but still the field have to transform, and it's kind of strange. So we will see that actually the transformation of fields is due to a property which is like the universality property, and the conformal symmetry, which is like, will actually tell you that if I actually look at my model through a conformal map, in fact, I can consider the same, I don't have to change the parameters to get actually the same limit when delta goes to 0. And at last, we have seen that in the abstract conformal field theory, there is a field which is important, which is the stress tensor. But, well, I mean, we know that it exists, but we don't know exactly what is, you know, what it is. I mean, what is he doing here? Okay, so I hope by like showing you like using statistical models and giving you a definition of the stress tensor, we will actually be able to link the stress tensor with a geometric property, and we'll see that actually if we look at some modes of the stress tensor, or integral, like contour integral of the stress tensor, it will tell you actually how the fields have to transform well when I change a little the background states. Okay, so those are the three things that I want to convey. It's really for now. So it's the fact that we will try to understand better the transformation law. So this will come actually from the universality property. Then we'll try also to understand better the conformal symmetry. So it will be something which tells you that actually the parameters of the statistical model won't change when I look at the system through a conformal map, and then we will try to link the stress tensor to the geometry, and thus to the transformation law field. So the stress tensor will actually appear really as an object which doesn't just pop out like that. It really have like a meaning. And then we'll have to show indeed that this object that we managed to exhibit, or that we'll assume that it exists, actually will show that indeed it should satisfy the OPE T with T, T with O, and we will recover actually the axioms of the conformal, the abstract conformal field theory. Okay. So is it okay? What is the goal for now? Okay, so we are going to consider statistical model, which actually depends on various parameters, like for example the temperature. So we are going to assume that there is a statistical model, and I will explain it so what is through examples, and we'll have some parameters. Okay, and we'll actually consider statistical models which have a certain property, which is that they have like a, oh yeah, usually I do this, sorry. View, close. So, okay, I will manage, close current view, and split. Okay. Okay, we consider models actually which with a second phase or order phase transition. So all the part I'm going to do here, it's I mean about phase transition and things like that. It's purely to an introduction on this. I'm not going to dive deep into that. It's just to give you some ideas or intuition why CFT is important at that for those kind of transition. But yeah, it's again another super big subject. So what is a phase transition? Well, a phase transition is just that you have a certain change of behavior of some quantities, thermodynamical quantities, when you look at them as a function of the parameters. Okay, so for example, you can have that like something called the magnetization. We'll see in Ising. The magnetization is actually equal to 0 when the temperature is high, and then suddenly it will increase. Okay, and it will be non-zero anymore. Okay, so you have like a change of this quantity, and the most important actually is that it's even not more analytic at this point. Okay, so we'll see that there is a power law at the moment when the magnetization begins not to be 0. Actually, there is a power law which is quite important. Okay, so a second order. So I have explained to you like kind of briefly what is a phase transition. So it's a model where there is a change of behavior of the thermodynamical quantities, and where those things are not analytical anymore. But I need to tell you what is a second order. A second order is actually when actually these parameters are still continuous. Okay, so it's more actually the derivative which will actually have some problem, but you don't have a gem. So we are going to see an example through the Ising model. So we are going to consider the Ising model, for example, living on the grid omega delta. So I consider exactly the same setup as the Gaussian free field. And in order to define the Ising model, what I'm going to consider is at any point on the grid, I don't have like a random variable which is real valued, but we have only plus or minus one random variable at each point of the grid. Okay, so at each point of the grid I have plus or minus 1, and this is called a spin actually at the point, and we write it like that, at the point x. Okay, and so the spin belongs to plus or minus 1. And what is the probability? So the probability of the configuration, so the probability of a configuration, so sigma x. So configuration is I give all the spins at all the points of my grid. So it's exactly kind of like, it's similar to what we have seen up to now. It will be of the form it's proportional to exponential minus beta and an Hamiltonian of sigma. Okay, and so what is the Hamiltonian here? So maybe somebody know about it? Does somebody know? No? Okay. So no problem. So we'll have to sum over all the neighbors, and we have to look at sigma x, sigma I. So which means we are looking at, okay, I am at x and I look at xy, I look at this edge and I look, okay, does the spin is line or not? Okay. So can somebody tell me actually what kind of configuration is, more going to happen?
They're gonna align themselves.
Okay, so they will they have to tend to align. So they will try to align. Okay, but of course there is this minus beta here. Okay, so there is a parameter here, and we see there's two things to say about beta. When beta is actually is actually super big, what happens? And when beta is actually close to 0. So close to 0, it's actually very simple in some sense. What's happening when beta is actually close to 0?
It's random, no?
Yeah, so to be more specific, what we have is that then this is kind of equal to 0, then this is equal to 1. So we are just saying that the probability each configuration has kind of all the same weight. Okay, so what we have here, we have just a uniform uniform measure in some sense. It's converging to the uniform measure on the space. Okay, on the configuration. Okay, so there's a lot of disorder in my system. Okay, and so that's, you see, it's kind of like if we were eating the system. Okay, so in some sense we are in a high temperature region. When beta is actually super high, what happens is that as soon as you are not at the minimal energy, what you have is that you will be killed. Okay, so what you have is actually you will have something where, for example, let's assume that we assume with boundary conditions. So we are going to consider the boundary conditions sigma x equals plus, for example, +1, make things simpler. So when beta is actually very huge, if my configuration doesn't have the lower energy, actually it will be kind of, it will disappear. And so what we see is just the minimum energy configuration, and we have seen like that it's actually, they tend to align, so it's the one where everything is aligned. So actually what we will have is just sigma is equal to 1. So sigma is actually equal to 1 everywhere. Okay, so we can see two things, is that there is actually two kind of regime. One where beta is really big and everything is frozen. It's like if the temperature dropped to 0, and then everything tends to align. And so, for example, if I have a point in the middle of my grid, it will actually feel the effect of the boundary. And when beta is actually close to 0, then we see that everything is disorder. It's like if we have a temperature which is super high and everything, you know, wants to move around and to be like not to align with everybody. And then if I am at the middle, actually, I don't feel anymore the effect on my the effect of the boundary condition. Okay, so actually we call beta the inverse temperature. So here we are actually in the low temperature regime, and here we are in the high temperature regime. And so here, any point feel really strongly the effect of the boundary condition, and here the points don't feel. I mean, no points feel. No point, like any point feel. Any points feel feels the effect of the boundary condition. Okay, so of course, I mean, you can imagine what's going to happen. Like I'm going from like beta super high to beta low. You know, there should be a kind of transition, okay, between the low temperature and the high temperature. Okay, so there is actually a beta critical. There is a beta critical where, well, you feel actually the effect of the boundary kind of, but not too much. Okay, so your spin will not be equal to 1 when you are looking at the point at the middle of the grid. The spin will not be equal to 1, but still it won't be totally random. Okay, and okay. So there were where there is a phase transition of order 2, of second order. Okay, So for like, yeah, so for some people actually, I mean, people see that as the fact that there's a fight between entropy and like minimization of the energy. When beta is actually kind of equal to 0, then it's the entropy which wins. When beta is actually bigger than 1, then it's the minimization of the energy which wins. And so there is at one moment something where there is a balance between everything. Okay, so let's see at the what does it mean exactly, the fact that there is this beta c. So the influence, like, let's look at the influence of the boundary on, let's say, 0, which belongs, let's say that 0 belongs to omega delta. Okay, so we are going to consider this, so the minimization at 0, which is the expectation of the spin at 0, at the point 0, and we are going to consider. So let's put something to make it even clearer. We are going to consider the spin at 0 on the grid omega delta, and we are going to consider the limit as delta goes to 0. Okay. So we are considering an Ising model on the grid with mesh is actually going to 0. We have plus boundary condition, and we are wondering, okay, what's going to happen when delta goes to 0? Okay, so of course, if you see here, if beta is actually very large, we saw that, well, sigma should be kind of equal to 1. Okay, so what we should see is that if beta is really, really huge, well, even when delta goes to 0, okay, you feel so much the boundary condition, even if you are far, that actually the spin will be equal to 1. The expectation, it will converge to 1. Okay, so we should expect that when beta is huge, if the limit of this when delta goes to 0 exists, it should be equal to 1, okay, at the infinity. When beta is equal to 0, we saw that it's the uniform measure. Okay, so when delta goes to 0, actually the expectation is the same as when delta is fixed, and it's actually equal to 0. Okay, because if my spin is uniform, it's plus or minus 1. Okay, the expectation is actually 0. Okay, so we see that if the limit of this exists, so we call that, and indeed it can show that it exists. So the limit of this delta to 0. So it depends also on partly on omega, but we don't care here. So we take the limit of that. We see that we should have that. So there is 2 points, is that m of infinity is equal to 1, and that at 0 we said it's equal to 0. Okay, so you see that actually this magnetization, actually it's 0, and then it goes somewhere. Okay, so what is interesting is that in fact, well, during a few time actually it will be equal to 0. Okay, so we can. So what is interesting is that we can consider beta c, which is the supremum of the beta, such that beta is positive, such that this is equal to 0. And so what is quite interesting is that we have that beta c is actually strictly positive. Okay, so which means that actually the magnetization is actually really 0 during a certain time, and then suddenly actually it will be strictly positive. Okay, so because actually it must also increase with, it's not difficult to see it, it should increase actually with beta also. Okay, so it's really equal to 0, and then at one moment it should be positive. Okay, now the question is, when you are at beta c, what is the value of m, and when you are just above beta c, what is it? So what happens is that in fact we don't have, we don't jump. Okay, the function actually m is continuous. Okay. So this is what we call, we see that there is a second phase transition, and let me draw actually what it looks like. The function m is, yep, it's walking. Okay, so I need to stop. Stuck. Sorry. Okay, it doesn't want to see anything. So. Okay, let me try again. Okay, so this function, let me tell you a little. Okay, so so the function looks like this. So we have here beta here, and we know that at infinity it should be equal to. You don't see anything. Okay. This would be kind of not nice if I cannot show you. I'm very sorry for that. Okay, let's hope it will. It's actually the cable which have a problem, and I don't know why. Okay, so we know that when beta is actually very large, it should be close to 1. Okay, but let me draw it. I will draw it, and then actually I will share it with you. Maybe it's better to do that. So that, okay, it will freeze, but it's not a problem if I've already drawn it. Okay. And we have beta C here. I'm very sorry. It's a problem of cables, and I don't know what to do. Okay, so let me try to show you again. When it freezes, at least I've drawn it. Okay, voilà. So this is actually how the magnetization looks like. Okay, it's equal to 0 until beta C, and then after it will actually grow, and then it will converge to 1. Okay. Now, what is actually even more interesting, is that when delta goes to 0, when you are actually before beta C, okay, you will converge to 0 exponentially fast. Okay, so expectation of the spin actually will converge exponentially fast to 0. When you are strictly bigger than beta C, also you will have extremely fast convergence to m beta. Okay, so what we have is when beta is actually smaller than beta C, or beta is actually bigger than beta C, the convergence is exponentially fast. Now, when beta is actually equal to beta C, well, the convergence is no more exponential, and we have the following fact is that this actually is kind of equal to a certain constant here that we don't care, and it's delta to the power 1/8. Okay. So, like, is it normal for you? I mean, are you really surprised or not about that?
I am a bit, honestly.
You're a bit surprised. Okay, but what is the goal of this lesson actually now? We said the goal is to show that, well, we can actually approximate any CFT with a statistical model. And we saw that, well, if I want to approximate the bosonic free field, I need to take like some polynomial recipes, you know, in like some, so here it was a big product. And then I had to multiply by delta to the power minus something. Okay, so first of all, if I was looking at the discrete derivative, d phi, okay, I had to look at delta minus 1 d phi in order to have a limit which was something not 0 or not infinity. Okay, so I mean, of course, we are looking at the Ising model, and one of the first field that we want to have, of course, is to consider a scaling version of this recipe here, of this field here. Okay, this is the easiest field that I have in my statistical model, and well, if I hope that I have a CFT limit and the scaling limit, well, and if I hope that I can do exactly the same thing as for the discrete Gaussian free field, well, I hope that I can have like delta to the power minus something such that delta to the power minus something times sigma is actually going to converge in correlation to something. Okay, it's exactly what we did for the discrete Gaussian free field. Okay, and here what I'm saying here when I write this is just it is just to say that if I consider this field here, delta to the power minus 1/8 of sigma at the point 0 and delta, this converge just for the wine points correlation function. So in some sense, I mean,
what surprises me is that it's the same exponent as the magnetization with respect to the temperature.
Yeah, so it's the same, but it's not. Okay, we are going to see that it's not totally the same. The magnetization is actually 1/8/1. This
okay,
one actually, but indeed they are linked, and I'm going to tell just you a little about that. Okay. But so can you guess already? Okay, if at beta c, I can do exactly the same thing that I did for the discrete Gaussian free field. Okay, which means that I can like look up some recipes such that when I scale them, I converge to something which is continuous, and that indeed at the limit it's a CFT. Can you guess actually what should be the dimension of the continuous field which represent the spin? Just to see if so last time what did we say about when we did the scaling limit of the discrete Gaussian free field? We said that in front of the derivatives we had delta to the power minus something, and this something was what?
Scaling dimension.
The scaling dimension. Okay, we saw that in this case it was the sum of actually the left and right dimension of the continuous field. Okay, and so indeed you can already like think, okay, in fact here the underlying continuous field will have a scaling dimension, which means like the sum of the left dimension and right dimension will be equal to 1/8. Okay, so when we write here this, okay, it gives us already some hints that okay, indeed we might be able to define a scaling limit. It has really like the flavor that we would like, and that we even know we have a guess already about what will be the scaling dimension of the field underlying the okay. So as Samuel said also, we know, so I'm not going to dive too much into that, but we know actually the behavior of the magnetization when beta is actually going to the beta critical, and when beta is actually bigger. Okay, so overset, no, underset, no, never the good right thing. Okay, so when it's actually bigger. Okay, so we consider beta goes to beta c. Okay, and we saw that actually it has to converge to 0, and what we have is that the magnetization behave like that. It's exactly what Samuel said. It's actually a constant times beta minus beta c to the power 1/8. Okay, so this 1/8 is called is a critical exponent. Okay, it's called a critical exponent, and there are different critical exponents when you are looking at a second phase transition, because well, you can look at different thermodynamical quantities. So first of all, I mean, you can look at you can add actually an external field and take the external field goes to 0, or you can actually, and we'll see that you can see the correlation lengths actually how it will diverge, and each time there will be some power laws, and these power laws each time there will be numbers which are actually rational numbers, and well, a little something maybe I will tell a little more about that. so you will have a class of different critical exponents. And what is very nice about conformal field theory is that there are some arguments based on renormalization group, which tells you that, well, if you know all the dimensions of the fields in your scaling limit CFT, then actually you can compute all the critical exponents. Okay, so you might have, for example, in Ising, typically there is like, okay, there's 5 critical exponents, but actually you have a lot of relations between them, and you see that actually there is only 2 critical exponents which are free. Okay, and actually those 2 critical exponents which are free, you can actually compute them using the 2 primary fields in the CFT, the 2 dimensions of the primary fields in the CFT, which are 1, 8, and 1. Okay, so I'm not going to dive too much into that, but it's really to tell you that, well, when you look at phase transition and second order phase transition, you will have some Power law which appears, which tell you the behavior of the different thermodynamical properties. The exponent actually will be rational numbers, and actually they will be functions of the dimension of the scaling limit CFT, of the primary fields in the scaling limit CFT. Okay. So if you are able to have a guess about the dimension of the fields of the primary fields in the CFT, then you will be able to guess actually the critical exponent. Okay, and this is very, very nice, because what we are going to see is that if you consider a statistical model and you look at the statistical, if you look at the CFT, the scaling limit CFT, it will satisfy a certain property, which is the unitary property. And this will actually tell you that you have kind of no choice about the dimension of the fields. Okay, so you know that if you manage to kind of pin down like what is the central charge, then there is a theorem which tells you if you have a unitary CFT with a central charge given by this much, which is smaller than 1, then the dimensions of the primary fields is equal to this, this, and this. You have no choice. Okay. So which means that we are going to be able to compute the critical exponent behavior of those quantities here near the critical exponents in plenty different models, just by actually showing that indeed they should be a CFT behind, indeed it should be unitary, and indeed I can have a guess, at least by doing some statistical some simulation, I can have a guess about what is the central charge. Okay. Before I stop, actually, I will make just a 5-minute break. Just let me tell you actually what is the beta C actually in the square lattice. Square lattice. The beta C is known, and it's actually given by 1/2 ln of 1 plus square root of 2. Okay. Okay, so yeah, we are going to stop here for 5 minutes. Then after, I will just maybe tell you 5 minutes a little more about the critical exponent if you want, a little about the different models, and to tell you actually, like, for example, the critical exponent here, which is usually called, so unfortunately, it's called also beta. Okay, so this critical exponent, you will find it's beta also. We'll see that. Yeah, what is the formula which links this beta and the dimension of the field in the Ising model? First of all, I can tell you, and we'll see that actually it means that it's actually equal to 1/8. Okay, and then we will see a little. So we have seen here that there is something happening when we consider a grid in a domain, and when we take delta, it goes to 0. But we see that we will see also that this phase transition, you can see it also, instead of taking delta goes to 0, you can take actually omega goes to C. It will be quite important to understand some little things, typically to understand what is the correlation length and what is the behavior of the correlations. And then when we have that, we'll just assume that we have a model, a statistical model on the grid Z2. Okay, and we will define what is a scaling, what is a local discrete field, what is a scaling local field, what is a statistical field theory, and we'll see already a few things about the correlation in the statistical field theory, and we'll see also, if we have time, how the fields react when we do a global conformal transformation of the plane, so translation, rotation, dilatation. and we'll stop there. Okay. So see you in 5 minutes. Okay, so everybody is here?
Yeah.
Almost, except Samuel. Ah, perfect. Okay, so as I told you, actually, so let me talk like just like 2 minutes about that. Oh, can I really? Yeah, well, I will just say again to what I said. So there are actually different critical exponents that you can define when you have like a such model where you have a second order transition, and each time it's actually power laws. Okay, it tells you what how does the explosion is power law, or how it goes to zero with a certain power law, and so there are like 6 critical exponents kind of which are important. For example, in Ising there is this they are called alpha, beta, gamma, delta, mu, and eta. So, I mean, for me, but I'm not inside this kind of domain. So, for me, the most important is actually the 2 last. So, eta is actually something which tells you actually when I look at the correlation function of sigma, how actually when I'm at the critical beta, actually how it decays. And you can understand why it's super important, because well, we have seen that if we have a field in CFT which has a certain dimension, then we know actually how the correlation decay when the points are far apart. And we know, I mean, and this decay is actually given by the scaling dimension of the field. Okay, so there is a critical exponent where instead of looking, 1 over r to the power delta, what you are looking is 1 over r to the power d minus 2 plus eta. In this case, d is equal to 2, so you have that eta is actually equal to the dimension of your field. Okay, so you have this kind of critical exponent here. When you look at the correlation function, there is another one where, and we are going to see it a little after, which is like how the correlation function explode. So the correlation function is correlation length. I mean, explode. Correlation length, in some sense, tells you how far the interaction actually in my system propagate. Okay? So typically it will tell you partly also like if I am at 0, does my boundary influence the spin at 0 and things like that. Okay, so it's really the how far the interaction goes. And well, the thing is that if you want to do a scaling limit and using polynomial scaling limit, then you see that this correlation length, and we're going to see it after, must actually be equal to infinity when you are at beta c. Okay, so you must have an explosion of the correlation length. So of the correlation length actually when at beta equal to beta c, and this is given by this exponent which is called eta. And this eta actually you can compute it using actually also the dimension, because it's actually just given by 1 over 2 minus the dimension of the energy. Okay, so we are going to see that in the Ising CFT there is 2 fields which are important: the spin field and the energy field. And the energy field will have a certain dimension, which is actually 1. And you can show that this eta, which is like how the correlation lengths explode, is actually equal to 1 over 2 minus delta. Okay. So of course there is the beta also that we said here. The beta, so unfortunately it's called beta also. It's 1 over 8, and then the formula is actually not, the 1 over 8 is not equal to this 1 over 8. If you use the arguments of the renormalization group, you have that this 1 over 8 actually it's equal to the dimension of the spin field over 2 minus dimension of the energy. But the thing is that we saw that, I mean, we will see that delta epsilon is equal to 1. So of course, you get only the dimension of the spin field, and here it's 1/8. Okay, so that's why you have a 1/8. But it's, if I'm telling you that, is that the relation are not trivial. Okay, it's not because there is 1/8 here that there is 1/8 here. Okay, in order to get this 1/8, you need know the dimension of the spin and of the energy. Okay. Okay, and actually there are other things like, for example, the specific heat, the susceptibility, and things like that. I'm not going to go into details. If you want to ask me a question, I have the relations later during the exam, during the question. I mean, the exercise we can do that. Okay. Okay. So this remark. Let's put a remark. So the 1/8 in the monetization is actually given by, it's actually given really by this formula here, and well, you have actually that it's equal to 1/8 because delta, because we'll see that this is equal to, okay. Okay. So what kind of, like, yeah, I can tell you just like that, maybe without really writing. There are other models where you have a second order phase transition. So first of all, you have one model which is called the Blume Capel model, and where you have, when the parameters are really well chosen, you have a model which is called the tricritical Ising model. So it's a model where the spin now is actually equal to -1, 0, or 1. Okay, and you will have exactly the same Hamiltonian here. You have this part here first, and then you will have another part. So in the Blume Capel model, sigma is actually, it's equal to -1, 0, or 1, and the Hamiltonian is actually equal to h of sigma is simply h Ising of sigma minus, so given how I wrote it, let's write it like that, minus a chemical potential, it's called V of sigma. So where V of sigma is actually something which tells you actually, do I have a spin or not? Okay, 0, you have to imagine, it means that you don't have any spin actually, and -1 and 1 is, so you have to imagine it's really the Ising model, but sometimes you don't have the spin, you allow the spin not to be here. Okay, and so what you have is, you will have a potential like that, and what you will have is that there is a beta critical, such that, well, if you have beta lower than beta critical, you will have a continuous phase transition when delta is growing. Okay, so you have to imagine I have beta and I have delta here, and I'm looking at the phase transition. So I can actually, maybe if it works, let's try. Yep. So you have delta here, you have beta here, and you look at the system actually with beta and delta, and you will have beta critical here. And what you will have is actually you have the continuous phase transition when delta, so you fix the beta and then you change the delta. So here you'll have a second order phase transition, which normally we think it looks like the Ising phase transition. Then above actually you have actually a discontinuous you have a discontinuous phase transition. So when you go from here to here, the things will actually jump. Okay, and there is one point here where actually, if you really manage to be exactly here, you have a continuous phase transition. But if you take the scaling limit of the system, you will not get the same CFT as the Ising model. Okay, so it will give you actually another CFT. Okay, and the same in that case, actually, you can show that the magnetization actually will decay to 0 with a certain power. The power will be actually 3/40. Okay, so again, a rational number, you see. And you can also look at the expectation of sigma 0 squared. Okay, so to know if the spin is here at 0 or not, -1/2, and this will also decay to 0, but with a power 1/5. Okay, so we have really we know kind of what are those exponents and how do we know them. Again, it's because we know that, well, it should actually converge to the CFT, and we know that this CFT should be unitary. We know kind of what is the central charge, and then we know actually what are the dimensions, and then, well, we guess kind of, because of some symmetries of the different fields, we can guess actually what are the corresponding discrete fields, okay? You have also another model, for example, which is the three-pots model, or the critical three-pots model. Okay, wow, super hard. Okay, three critical three-pots model, where actually the spin now is going to leave. So you have two different ways to see it. It will be actually not 1 minus 1, but it will be actually 1 j bar, which are the roots of the unity. Okay, and Hamiltonian now, it will be something of this form. I'm just going to write it here because I mean it's just for you to know, kind of, to have a guess about, like, to understand a little more, but it's not super important. We are not going to use it anymore after. Okay, so the Hamiltonian will be something like that. So again, it's an Hamiltonian like where the spins tend to align. Okay, but now you have still 1 minus 1 and like 1 j and j bar. Okay, and you can see that in fact it's actually equivalent to considering just spins with a, b, c. So let's say minus 1, 0, and 1. So it's really equivalent to look at a spin which takes 3 different values, and with an Hamiltonian which is of the following form, you just ask sigma x to be equal to sigma y. Okay. So you can really see that indeed, if I write it like that, you see that they really want to align. Okay. And so again, I actually have a second order phase transition. And again, what you see is that m beta will be of the form b minus beta c to the power now 1/9. Okay, and what you know is that also is that this actually should decay as c delta to the power 2/15, and you know it again, like, I mean, one way to know it is because of the CFT property I told you, and you know also that expectation of sigma a squared minus constant is equal to c delta to the power 5/4. Okay. So now actually, if you look here, the equation I had here, normally you should see that they match, everything match here. Okay. Okay, so those things was like what I wanted to really make you understand is that, well, there are systems which depend on parameters. When the parameters actually come close to some critical points, actually, the battle between entropy and minimization of energy actually became like even, and we have some critical phenomena happening. You have like you will have actually explosion of certain quantities, or you will have actually those kind of properties here with power laws. Okay, and so the magnetization will actually have some power laws. It will be 0, and then it will actually grow without actually being discontinuous. Okay. And those power laws actually, you can actually guess what they are if you manage to understand what is the CFT behind the system. And you do that by doing the following, saying, okay, actually, my model has some properties, or I believe that he has some certain properties, like universality and things like that. And because of that, I can believe that there should be a CFT behind. I should be able to scale and to have scaling limits of my system at the critical parameters, and then I should have a CFT. We'll see that in this CFT we should have some unitarity property, which means that in fact there will be some scalar product which will be very natural in the statistical model, but it will actually will allow to define a scalar product in the CFT also, such that well, there is a property called unitarity, which will be a true for this kind of CFT. And because of that, we'll see that there is a theorem which tells you, well, if you know what is the central charge, and the central charge is less than 1, then actually you know exactly what are the different dimensions of the field, of the primary fields that lives in the CFT. Okay, And once you have that, actually all the critical exponent can be computed using those dimensions. Okay, so it's really important to have a guess about those dimensions because it really allow you to have some intuition about what will be the critical exponent in your system. Okay. And I think, I mean, for me, I think it's really amazing because it means that, and you will see it, it means that this 1/9, for example, we can guess it just using this theorem I told you about unitarity, which is actually an algebraic theorem. Okay, it's actually a theorem which tells you, well, in fact, on my CFT, I will have some representation. It will allow me to define some representation of a certain algebra, and this algebra, which will be actually unitary. Okay, will have the unitary property in this representation, and we know that actually it will be really an algebraic theorem which tells you, okay, if I have this algebra which acts on this space and it satisfies the unitary property and the central charge is smaller than 1, then the highest way or the dimension is actually given by either that or that. Okay, so I think it's really, really amazing that, okay, we are considering something which is probabilistic. We are going to define we are going to see why it leads to some kind of CFT. We will see why it leads to some representation theory of a certain algebra, which is called the Virasoro algebra. And we will see that there is some number which appear, which are those kind of 2/15 or 4/5, which appear naturally. And then using so this part we won't do, but using the randomization group techniques, physicists know actually how to relate those exponents with those exponents here. So which means that we'll be able to guess something about physics and probabilistic model using actually algebraic properties, which I find really kind of amazing. Okay. So everything is fine?
I had a little question.
Yes.
Do we know how many fields there is? Like, for example, this sigma and energy field. Like, do we know how, if there's, seems like there's only two for
so typically what we will have is that, well, you can guess because if you take a statistical model, you will be able to, you know, I mean, you will be able to guess, if there is a second order phase transition, you know that there will be a CFT behind. Then since it's probabilistic, you know exactly, if I know the central charge, I will know actually what are the dimension, okay? And then you get guess what is the central charge by either doing simulation or things like that. And so you can guess what are the dimensions that you should get, what are the fields then that you should get, and then after using some kind of, so for example, for the Ising CFT, which means I take a CFT, which is unitary and with central charge equal 1/2. I know that, for example, I know that the scaling dimension is 1 or 1/8. I don't have any other choice. Okay, so I have a field epsilon, I have a field sigma. Epsilon is of dimension 1, and sigma is of dimension 1/8. Okay, of scaling dimension 1/8. Then what I can guess is, okay, if I want to understand what are those fields, I'm like, okay, I look at the correlation of sigma and I see that actually they have some property when I do a flip. Okay, so I will have some certain property according to the flip. So if I take minus of my model, then things, I will have sigma transforming to minus sigma and things like that. Whereas epsilon actually won't see actually the flip. And so I know that I should have a field which is invariant under the flip and another one which is which follows in some sense the flip. Okay, so then I'm like, okay, so they should be sigma in my discrete setting. I have the field sigma, which is natural. And then, I mean, what is the next easiest thing that I can do? Well, it should be sigma squared, for example, but sigma squared is actually always equal to 1. So it's not good. Then, so it's maybe the multiplication of sigma x with sigma x plus delta. Okay, and so, and I look at this field and then I see that indeed, actually, it should satisfy the good things. So actually, it's really, I mean, so my point is, the dimensions, you can guess some properties of the fields at the continuous limit. So you can guess some properties of the fields on the discrete predecessor. After, to exactly get the good thing, it's always a trial and guess and things like that. Okay, and at one moment you have to believe that, okay, you're right. Okay. But of course, I mean, it's what I'm going to say all after. It's a kind of, I mean, it's still conjectural. That so I'm going to tell you, I'm going to put a conjecture at one moment, which is take all the local fields that I can do with polynomial functions, scale them, and look at all of them, which actually have a limit in terms of correlations when you take just insertion of this field all around. You call that scaling local fields. And the conjecture is that all the scaling local fields actually give you all the fields of the CFT, and that you cannot, I mean, that, yeah, you cannot cook up other fields than the one given by the CFT. And voilà, and after, I mean, it's just you try, you know, the simplest one you can have. So the only one which, so the only two fields that, or three fields, let's say, that it's very easy to guess each time, it's like the spin, of course, because it will be just the spin, is the stress tensor, because we will see a definition of it, which actually really gives you an intuition about what it is on the discrete level, and you can kind of compute it using that. And there is also the energy, you know. And after, I mean, it's I mean, from what I know, it's more, you know, you try, you guess, you try to imagine what's going on, and voilà.
Okay.
Okay. So, and typically, I mean, if you look at books, it's never written. I mean, you never know. In fact, you know, books they just work with CFT. Okay, so they tell you, okay, there's those fields, but they don't tell you, okay, but it correspond to what actually on the discrete level. There are even people who do Ising CFT without knowing that it's coming from a Ising model. Kind of, I mean, they don't care. They just do Ising model, Ising CFT. You know. So it's kind of, I mean, what we are doing here, it's really new, in fact, and the thing we are putting in the books, it's really, I mean, if we want to do this book, it's really because it's something missing, the fact that, you know, to really have some intuition about the link between the discrete level and the continuous level. Okay. So it's still like a lot conjectural, of course. Okay. Is it okay?
Yes.
Okay, so let me say a little something about the phase transition in the Z limits, Z2 limit for the Ising model, let's say. So what we were interested in, it's really what we were interested in for now, it was like I take omega and I take grid and then I take the mesh, goes to 0. Okay, but when I do that, actually, you see that, well, when I have something with a certain mesh here, delta, in fact, actually, I can blow up everything and I can say, okay, in fact, what I'm looking at is the usual grid size 1, and then I have omega, which actually goes to converge to C. Okay, so it's quite natural to, I mean, to think a little about, okay, what's going on when we look at this picture here. Okay, so when I look at this picture here, I really have delta fixed, and then I take omega goes to 0, and we look at this model. Why is it even more interesting for us? It's that, well, I don't want to talk about CFT on a domain. I want to talk about CFT on the plane. Okay, it's what we did. Okay, so we could introduce on the domain, but it's much harder. So I want to define it really on the plane, and so of course my model must live on the plane. Okay, so at the end, I mean, what we are going to look, it's really the model on the plane on the grid Z2, and still we are going to take the scaling limit by looking at delta Z2. Okay, but I really want to look at the model on the plane. Okay, so what's going to happen actually if I look at the Ising model where I have, like, let's say, plus boundary condition here. Okay, so of course, again, if beta is actually, so we saw it above, if actually beta is actually very large, what I see is that, well, I feel already a lot the boundary condition. Okay, so all my spin will be mostly equal to 1, or actually they will really feel, okay, they will really feel the boundary. Okay, and when beta is actually close to 0, I won't feel the boundary. What does it mean? It means that, well, if I try to define what is the Ising model on the plane, well, what I want is to take the domain goes to infinity, but of course I have to give a boundary condition. And what will happen is that depending on beta, I will have something like different behaviors. If beta is actually greater than beta c, do you think that there is a difference if I put plus boundary condition or minus boundary conditions?
Yeah, yes.
Yes. Okay. So if beta is actually greater than 1, we say that, okay, it's frozen kind of. So if the boundary is plus or if the boundary is minus, well, I will feel actually this boundary. Okay. So typically when I will try to define the Ising model on the plane, well, the two boundary will be really different. And so what we have is that we'll have actually many different measures when we want to define the limits z goes to like omega goes to c. Okay. Now, actually, if I am below beta c, then I don't feel at all in some sense, but I kind of don't feel the boundary. And of course, since the boundary is going larger and larger, okay, then I feel even less the boundary. And so actually I will have only one measure, which will be not very interesting. Okay, one measure, but not really interesting. And actually at beta c, I will have only one measure. So when I say one measure is that no matter what I put on the boundary, actually, when I take the limit, actually it will define actually the same probabilistic measure on the spin field. Okay. So at beta c, I will have one measure which will be interesting. Okay. So you see that the phase transition also appears not only when we take a scaling limit delta goes to 0, but also when we take actually omega goes to infinity. Okay. So what we are going to consider now is really, and in the later when I will talk about, like, I consider a model on Z2, what I'm going to assume is that we have considered a model of the form exponential minus beta in Hamiltonian, which will be like of this form here, like so, which is like a sum of polynomial things around x. Okay, and then I will assume that if you are at the parameters, at the critical parameters, and add that this critical parameters, you don't care about the boundary that you put, and that you can really take omega goes to infinity. So you can really look at the model on Z2. Okay, so this is the assumption I will consider when I consider a model. On Z2, I will really assume that it's like the Ising model. At beta critical, I will have only one measure, and so I can define my model. Okay, now you see that. So which means that I will have a model on M2, on Z2, I will have a model here. And then what I want to do still is to take the scaling limit. So if you have a model on Z2, of course, you can define a model on delta Z2. So if I have a model on, let's go here, So what we have said is that if beta is actually, so yeah, we will assume that we are in the same setting as in the Ising model, which is that we can define the limit of the model on Z square as the unique measure obtained by putting any boundary condition, and taking omega goes to C. Okay, so we are in this case here, and now what we want to do, and so valid at beta critical. Okay, and we want to consider the scaling limits. So we consider a model on, so let's say the Ising model on Z2, and of course if I manage to define the Ising model on Z2, we can define it also on delta Z2. And how do I do that? well, what I just need to do is, if I have delta of x, I just say it's delta of sigma of delta x. Okay, so that's a scale. I scale really, really everything. Okay. Okay, so I can actually consider the model now on finer grid. Okay, and you see that what I'm really interested in is to fix in this grid here. What I want to do is actually to fix really complex number x and y, which are actually fixed and doesn't depend on the grid. And I will be, first of all, interested in the correlation of the field at x and at y. I will be interested in looking at this kind of stuff, like x sigma delta y. First of all, I will be interested in computing this kind of things. Okay, so I want to know how does this thing behave when delta goes to 0. But of course, what I can do is I can blow up everything again. Okay. And so instead of looking at a mesh delta here, I can look at the system on Z2. But now y is sent on what? It's sent actually on 1 over delta y, and x is sent on 1 over delta x. Okay? So trying to understand, so what I mean is that trying to understand this thing here in the scaling limit, it's kind of, it's similar to trying to understand this kind of things here, but in the Z2 grid. Okay? So using the scaling, so trying to understand what I said is trying to understand the expectation of sigma delta at a point. So, okay. So here, let's call that, yeah. Okay, there's this stuff that here it's really a point of the grid. And here I'm going to consider, so here it's really a point of the grid. So it, or I will write it certainly. So here it's really on the grid. And here I will use Z and Z prime, let's say. So here they are not on the grid. And of course, when I write sigma delta of Z, I mean, it's, I look at the point just, you know, near. So trying to understand this is actually kind of the same as trying to understand sigma, but at the point Z over delta and Z prime delta. Okay. Okay. So in particular, so typically, if you want to understand, like usually you don't want to understand that. Mostly you want to understand actually, let's say this kind of things instead. So if you want to if you want to understand actually the variance like that, then it's the same as trying to understand on this on the Z grid, but now you have to scale the points. You have to scale where are the points. Okay. So you understand that? What I'm doing. So in particular, there is something interesting, which is that, well, there's a notion for a system on Z2, which is the correlation length. Okay. So if the system has a finite correlation length, so on Z2, it means that this thing, this correlation, like this 2-point function, sigma x, sigma y minus, so the same, but this actually decays as something like exponential minus the distance between the two over correlation length. Okay. So there exists. So I search that of the system. So this here really is the system on Z, on Z2. Okay. Okay, so having a finite correlation length, it means that, well, if I look at the truncated or the cumulant or the variance of sigma x and sigma y, when x and y goes to, when x minus y, so the difference minus y goes to infinity, then I have decay like that, which is exponential. Okay. But if I have a finite correlation length, what I see is that, well, I can plug here. When delta goes to 0, then this and this actually goes far apart. Okay. So I can apply actually this formula here, but instead of x and y, I have to apply it to z over delta and z prime over delta. So in that case, what we have is that the thing on the left here will be actually equal to this, and here I have to put z prime, and I have to put also delta. Okay. So you see that when delta is going to 0, actually this is going to infinity, this is going to minus infinity. So this is going to 0, but exponentially exponentially quick. Exponentially quick. Okay. So you see that if the system actually has a finite correlation length, then this 2-point function actually goes to 0 exponentially quick. But is it actually good? Is it something that we hope? Zakaria? Excuse me? No, because?
Because that means there's well, there is no order at all. I mean,
yeah, and well, what it means is that we wouldn't be able to do like what we wanted to do for the to replicate what we did for the Gaussian free field, which means that what we want is to say, well, if I multiply this by delta to the power something, this by delta to the power something, I should get that all this goes to a finite number. Okay. But if all this goes exponentially quick, I cannot multiply by delta to the power something and get something finite and which is not equal to 0. Okay. So if the correlation length is finite, for sure we cannot define the scaling limit the way we wanted by just scaling the fields with a delta to the power minus a scaling dimension. Okay. So which means that in fact, in all the models we have to, so we want to consider, we must have that the correlation length is infinite. In that case, what it means that actually the decay is no more exponential here; it's actually polynomial. Okay. And indeed, this is the case when we consider a second order phase transition. Okay, so typically I told you that if you look at the correlation length for the Ising model, okay, then you have or it's even actually more general, I think. The decay is so it will explode, and it will explode like let me take again the formulas. So it explode like beta minus beta square beta critical to the power minus 1. So this minus 1 again, it's a critical exponent, and this critical exponent is just given by 1/2 minus 2 for the Ising model. It's 1/2 minus the dimension of the energy spin of the energy field. But the dimension of the energy field, we saw that it's actually equal to 1. So it's 1/2 minus 1, which is equal to 1. Okay. So the models we consider at the second order phase transition, actually, we will have that the correlation length is actually infinite. And this is a good news because it means that, well, we are not in the finite case where actually we know that in finite case, we cannot have the scaling limit as we want to consider. Okay. So to wrap up a little this part here, what we have seen is that so what we want to do now is already to understand better the axioms of conformal field theory using the statistical models. We have seen that the statistical models which are interesting for us are the one which have a phase transition which is second order. We gave an example which is the Ising model with minus and plus one random variables, where the Hamiltonian actually makes us is such that the spins try to align, but there is a parameter beta which actually control how it's important actually to minimize the energy. And so if beta is actually large, in fact, you will tend to actually freeze, and you will tend to actually minimize the energy. If beta is actually not equal to zero, it's actually close to zero, you tend not to really care about the energy. And then it's actually the entropy which is important. And so you will tend to actually see a uniform measure on the configuration. Okay. And we saw that then there should be actually a point at the middle, which is the critical beta or the critical inverse temperature, where actually something special should happen, where it's not really it's not really a disorder, but it's not totally neither frozen. Okay. And we saw that in fact we can really mathematically see that by considering the magnetization, which is the limit of the expectation of the spin at zero when the mesh goes to zero. And we saw that it should be equal to 1 at infinity, 0 before, and we saw that actually it's actually equal to 0 until a certain moment, which is actually this beta critical. And after this beta critical, it's strictly positive, but there is no jump. Okay. And the behavior of this magnetization at beta critical is given by a certain Power law. And this Power law, as I told you, can be actually computed if you know the dimensions of the field, of the primary fields of the CFT, which describe the scaling limit of the Ising model. Okay. I've told you also that there are other models, like where you can have more than like a spin which takes -1 or 1. You can have actually 3 states, for example, with the Blume Capel thing. And what we have seen also is that it's not only the magnetization which should actually behave in a certain way, but also the correlation length. Because if you consider the grid Z2 and you cut it somewhere and you take a boundary condition here, when beta is actually very low, then you won't feel the boundary. So if the boundary, so whatever the boundary is, actually it will be kind of random in the middle. When beta is actually large, the temperature is actually low. So you will feel the boundary, and you will feel it really even when the boundary is far, far, far. And so, which means that when beta is bigger than beta C, you will have the choice you will have to choose actually what is the boundary condition that you have to put. When beta is smaller than beta C, you don't care about it. And when beta is equal to beta C, fortunately, you don't care about it. And you can define actually a unique measure, which is this Ising model on the grid Z2. Then we have seen that what we are interested in is really not, it's not really the model on Z2, but it's on the scaling of Z2. Now, we want really to take Z and Z prime, which are fixed numbers, which are fixed complex numbers. And we want to study, like, for example, we will have to study at the moment correlation of this form if we want to show that indeed there is a scaling limit. Okay, we will have to consider this kind of stuff and to multiply it by delta to the power something. Okay, but if you consider this model here, this sigma delta, it lives on the grid delta Z2. Now I can actually blow up everything, and I can say, okay, but I can either write this as a measure, as an expectation of a spin which lives on delta Z2 at point Z or Z prime, or I can see it as expectation of the model sigma on Z2, but at point Z over delta, Z prime over delta. And so you see that you have to understand what's happening when 2 points are actually going far apart. Okay, and this actually is this behavior is actually captured by the notion of of correlation lengths, and it's in a system on Z2, it has a finite correlation length if you have decay which is exponential. Okay, but if you have a decay which is exponential, it means that when you will take the scaling limit, actually this will decay exponentially in delta, and this is not nice. This is not what you want. Okay, so you see that in fact in the models that if you want to have a scaling limit, the model must have an infinite correlation length. If you want to define a continuous limit, scaling limit, it's only possible when you consider a statistical model with infinite correlation lengths. Fortunately, actually at this phase transition, you have indeed that the correlation lengths will actually explode, and so it will be infinite, actually at beta equal beta c. And I told you again, the explosion here, the rate of explosion is again another critical exponent, which can be actually computed using the dimension of the continuous fields of the CFT of the scaling limit of the system. Okay, it's a 1/2 minus the dimension of the energy spin of the energy field, which is actually equal to 1. Okay, so let me just say a last thing to tell you. Okay, what we are going to do next. So unfortunately, I was hoping that we would do more, but yeah. But tell me actually if I go too slowly or too fast or thing like that. Yeah, I really need you to tell me. Okay, if there are things that I can go faster, you tell me. If there are things you don't understand, we can go slowly. Okay, so now from now on, let me like write really what is the setting, and then we will stop here. So the setting now is the following. We are going to consider a model M, a statistical model M, on the grid on Z2, which is obtained. And this, I'm not going to tell you why. I'm not going to tell you if it is possible for anything. We are assuming that somebody arrives and say, okay, me, I don't know anything about CFT. I don't know anything about things like that. Me, I'm just doing statistical models. I have managed to show that I have a model and I can define it on Z2 without need of any boundary condition. Okay, what can you do with that? Okay, so it's obtained by the limit as omega goes to C of a statistical model on omega cap Z2 with the measure, the underlying measure, which is of the following form. So of course it's proportional to, I'm not going to tell you each time. Sigma, where sigma is so where sigma here, it's something defined on this, and which takes finite values. Sigma this back to a certain set. Okay, so it's really the generalization of the Ising model. Okay, I have sigma, which takes finite value at any point of my grid, and I assume that I have some parameters. Okay, I will have some parameters inside the H that I'm not going to explicit, and I can really tweak the parameters so that, well, I don't need to, well, I am exactly at the phase transition of the system. Okay, so we are going to assume that H of sigma is of the following form. It's actually equal to sum over X of a certain thing F of X sigma Y, where Y is in the neighborhood of so Y minus X. So let's say more like this: X plus Y is in the neighborhood of X. Okay. Okay. So here you can have parameters. For example, it's here that I'm hiding the beta. I could hide the delta for the Blume Capel, first of all, or things like that. So we are going to assume that the Hamiltonian is of this following form. We have a polynomial function. So it's a polynomial function here of the spins near x. You are applying kind of the same formula everywhere, and you sum over all the x. Okay? So you can see that the Ising model is really like that. The Blume Capel, all the Hamiltonians I gave you, they were all of this form. Okay. So in particular, why do I want something like that? It's because the model, I'm sure that it will be translation invariant. Okay. Okay, and once you have this model here, what we are going to do is we consider the scaled models, which will be defined, which will be denoted by m to the power delta on delta z2, such that, so with spins, so now the spins, they are called sigma delta, so as I said, sigma delta of delta x is equal to sigma of x for x in z2. Okay, so you are just scaling, the grid. You don't touch the sigma. You just, you don't touch the sigma. You just, scale the grid trivial. Okay. Now, the questions that we are going to try to answer, it's what does it mean to consider the scaling limit, and we'll see that the underlying object will be a statistical, what we call a statistical field theory. Okay, so you can guess already, it's a field theory, so you know already what is field theory, but it's statistical because we want it to be the limit of a statistical model. Okay, so when we say statistical field theory, it's really this. It's really, we say the scaling limit actually is a statistical field theory because it will be first a field theory, which means we have symbols, we have correlations and stuff like that. But actually all those correlations can be obtained as limits of correlation in a statistical model. Okay, so what does it mean that? And what properties in the discrete model would lead us to the fact that the limit is a CFT. Okay, and the main properties that we will need is the following, and it's really this which will give us a lot of insight about CFT, is the universality property. So let me tell you a little about it. We have taken the grid and we are scaling it, and we have a continuous object. Now, well, why did we take the square grid? Okay, so the universality property tells you that, in fact, the limiting object, you could have get it by taking any other kind of grid, as long as it's not a horrible grid. You can take any like hexagonal grid or anything like that, or even you map the square grid by a diffeomorphism, for example, and you get another grid. Okay, so you could have, actually, the universality property tells you could have taken actually this grid, which is like deformed, and you could have actually changed the parameters, and you could have changed actually, the discrete local fields that you are going to consider. And if you could have done that such that when now you take the limit, you get exactly the same model. Okay, so it's really to say that you don't really care about the grid that you're considering. You could have taken other grids, and you could have actually get the limiting object by taking other limits. Now, the really important thing is that the other, okay, I'm not taking the same limit. I will have to take other limits, and I will have to trigger the parameters. For example, the beta, I will have to change the beta. For example, even on each edge in the Ising model, I might have to put a beta, which depends on the edge and things like that. Okay, but the universality property tells you, okay, in fact, you could have done that, and it's because of this universality property that we will first be able to define what is the conformal symmetry of the problem. It's really something which tells you that, okay, if my grid actually was the image of the square grid by a conformal map, then I don't need to change the parameters. Okay, this is really the symmetry behind the CFT. And we'll see also the transformation law appearing because, well, if I change the grid, I won't be able to take, the same recipe. Like, first of all, the derivatives, I won't be able to take exactly the same kind of derivatives. So I will have to change actually the fields that I'm considering. Okay, so because of that, we'll see the transformation law and the conformal invariance of the parameters. And then we will see that we'll have to introduce the stress tensor as an implementation of the deformations of the background space. So it will be another thing which will tell you, okay, actually, if I modify my grid, like I told you, like, okay, I could have taken another grid, but there is also something I could do is I can wonder, okay, if I take exactly the same model, but I kind of change a little the grid, okay, what kind of things do I have? Okay, and actually by changing locally a little the grid, then I will have this, I mean, I will have to introduce the stress tensor in order to compute what is the correlation I get. Okay, so next time we will see that. We'll see, so next time, I mean, you will have ready to tell me if I have to go fast or not fast, because next time we will see things that we have almost seen. Like, I mean, I did everything so that, I mean, now it's supernatural. We'll see what is a discrete field, a discrete lattice field. We'll see what is a discrete scaling local field. We'll see what is compatible family of discrete scaling fields. It will allow us to define what is a statistical field theory. And then we will actually see that in a statistical field theory, we have already informations about the correlations. Okay, we know already that 1-point correlation are translation invariant and 0, except if the scaling dimension is 0. And we will see also that you have a scaling behavior of the correlations, so you can compute the correlation of any field OX or Y. You will know that it's exactly the same formula as for the CFT. Okay, but you won't be able to get the 3-point function. Okay, up to now. Okay, and then we will see the action of the rotation also, and so we'll see the notion of spin, and possibly we'll next time if we do that. Let's hope we can do this, plus we can do already the university property, so that this will be lesson 8. Lesson 9, we can do maybe the stress tensor and showing that you have the word identity for the stress tensor. Lesson 10, maybe we can do the Virasoro algebra, the fact that you have the Virasoro algebra, and possibly to talk a little about the unitary, and 11 about the theorem of a unitary representation of Virasoro. And is it like 11 lesson or 12?
13, I guess.
13? Ah, okay, super nice. Okay. Yeah, no, super nice. It's not 13? Yeah, and I think there is something like it's not the same amount of lesson and exercise, something like that, you know. So possibly it's 12 lessons and 13 exercise. I remember there was something like that. Okay. But so yeah, the 11 will have that, and the 12 either will be slow and it will be used to finish this, or if I can, I will try to talk. So at the 11, we will be able to know a little more about the dimensions and things like that. And the last lesson, either it will be about getting some, computing the 4-point function, for example, because this is nice stuff, or trying to link it with the SLE, for example, the link between a Schramm-Lohner evolution, so which are like process, like curves, random curves, and conformal theory. So we'll see. Either we'll do the 4-point function or the SLE.